At the exact center of our galaxy lurks a monster weighing 4 million times more than our Sun. For decades, astronomers could only glimpse shadows of this beast through veils of cosmic dust stretching 26,000 light-years thick. Then the James Webb Space Telescope turned its golden mirrors toward the forbidden zone. What it revealed shattered everything we thought we understood about supermassive black holes. Stars are being born where physics says nothing should survive. Matter is behaving in ways our equations cannot explain. Ancient light is telling stories that rewrite galactic history. Scientists are now questioning whether Sagittarius A star is sleeping, awakening, or something far stranger than either possibility. The center of our galaxy just became the most mysterious place in the known universe. If you enjoy exploring our galaxy and the discoveries that are forcing scientists to rewrite textbooks, hit that like button and subscribe. Now, get yourself comfortable. Let's begin. Something massive lurks at the heart of our galaxy. You cannot see it with your eyes. No telescope viewing visible light can pierce the cosmic curtain, hiding it from view. For most of human history, we stared at the bright band of the Milky Way stretching across dark skies without knowing that the densest concentration of stars marked the direction of a gravitational monster beyond comprehension. The object is called Sagittarius A star. That name sounds almost casual for something weighing 4 million times more than our Sun. Scientists added the asterisk to distinguish this radio source from other emissions detected in the constellation Sagittarius. What began as an interesting radio signal discovered in 1974 became the most studied invisible object in modern astronomy. To understand why James Webb's observations shocked the scientific community, you first need to grasp what hides at the galactic center and why seeing it clearly required the most advanced space telescope ever constructed. Sagittarius A star sits approximately 26,000 light-years from Earth. This distance sounds enormous until you realize our galaxy spans 100,000 light-years across. We occupy a position roughly halfway between the center and the outer edge, nestled within one of the spiral arms that give our galaxy its characteristic shape. The galactic center lies in the direction of the constellation Sagittarius, hence the name. But here is where things become complicated. Between Earth and the galactic center stretches the densest concentration of cosmic dust, gas, and intervening stars in our entire cosmic neighborhood. Light traveling from the galactic center toward Earth encounters obstacle after obstacle. Visible wavelengths scatter and absorb as they attempt to penetrate this cosmic fog. The dust particles blocking our view are tiny, often smaller than the thickness of a human hair, but trillions upon trillions of them create an impenetrable wall. If you could somehow remove all this intervening material, the galactic center would blaze brighter than any other region of the night sky. Millions of stars crowd into a volume smaller than the distance between our Sun and its nearest neighbor. The stellar density near Sagittarius A star exceeds what we experience in our solar neighborhood by factors of millions. Stars orbit so close together that their gravitational interactions create chaos on timescales of mere centuries. Consider what this means for perspective. In the solar neighborhood where Earth resides, the average distance between neighboring stars measures roughly 4 light-years. You could fit entire solar systems between us and the next closest star. Near the galactic center, stars pack together so tightly that dozens occupy the same volume our Sun enjoys in solitude. Gravitational encounters that would take billions of years in our region happen within mere thousands of years there. Scientists first detected unusual radio emissions from this direction in 1932 when Carl Jansky built a radio antenna to study atmospheric static, interfering with transatlantic phone calls. He discovered that some of the noise came not from thunderstorms but from space itself. The strongest signal arrived from the direction of the galactic center. Jansky had accidentally invented radio astronomy and glimpsed the first hint of what lurked at the heart of our galaxy. Jansky was working for Bell Telephone Laboratories, trying to identify sources of interference that plagued early radio communications. He built a rotating antenna array mounted on wheels from a Model T Ford, earning it the nickname Jansky's merry-go-round. As he catalogued sources of static, he noticed one persistent signal that seemed to follow the stars rather than the sun. The signal peaked when the antenna pointed toward the constellation Sagittarius. The implications were staggering. Something in deep space was producing radio waves detectable from Earth. Jansky published his findings but never followed up with dedicated astronomical observations. The discovery languished until after World War II, when radar technology developed during the conflict was repurposed for astronomical research. Decades of radio observations followed. Each new telescope with improved sensitivity revealed more detail about the galactic center region. The emission called Sagittarius A turned out to contain multiple components. Sagittarius A East is a supernova remnant, the expanding debris from a stellar explosion that occurred roughly 10,000 years ago. Sagittarius A West is a spiral-shaped structure of hot gas that resembles a miniature galaxy orbiting within the larger Milky Way. And at the very center of it all sits Sagittarius A star, a compact radio source no larger than our solar system despite containing the mass of 4 million suns. The discovery of Sagittarius A star as a distinct radio source came in 1974 when astronomers Bruce Balick and Robert Brown used the National Radio Astronomy Observatory's interferometer to resolve the central radio emission into separate components. They found a bright, compact source that stood out against the diffuse background. This source measured less than 1 astronomical unit across, smaller than the distance from Earth to the Sun, yet produced radio emissions suggesting enormous energies concentrated in a tiny volume. What could pack so much energy into such a small space? The answer seemed obvious to some astronomers even then: a black hole. But confirming this hypothesis required measuring what surrounded the compact radio source. If a supermassive black hole lurked at the galactic center, nearby stars would orbit it at tremendous speeds. The orbital velocities would reveal the central mass through simple application of gravitational physics. The breakthrough that confirmed Sagittarius A star as a supermassive black hole came from tracking individual stars orbiting around it. Beginning in the 1990s, 2 research teams led by Andrea Ghez at the University of California, Los Angeles, and Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics used infrared telescopes to peer through the dust and monitor stars near the galactic center. Infrared light with wavelengths longer than visible light can penetrate dust clouds that block optical observations. This property made infrared astronomy essential for studying the galactic center. The same dust grains that completely absorb visible light allow infrared radiation to pass with only modest attenuation. Infrared telescopes effectively see through walls that are opaque to optical instruments. Both teams faced enormous technical challenges. The galactic center lies so far away that even with the largest telescopes, individual stars appear as tiny points of light. Measuring their positions required precision exceeding anything achieved in previous astronomical observations. The atmosphere constantly distorts incoming light, smearing those tiny points into blurry blobs. Techniques called adaptive optics, which use deformable mirrors to correct atmospheric distortion in real time, proved essential for achieving the necessary resolution. What these teams discovered over years of patient observation changed astronomy forever. Stars near the galactic center move incredibly fast. One star designated S2 completes an entire orbit around Sagittarius A star in just 16 years, while traveling at speeds exceeding 15 million miles per hour. At its closest approach, S2 passes within 17 light hours of the central object, roughly 4 times the distance from the Sun to Neptune. Think about what this means. A star similar in mass to our Sun whips around a complete orbit in less time than it takes a human child to graduate from elementary school to college. The orbital velocity at closest approach reaches 3% of the speed of light. No star in the solar neighborhood moves anywhere near this fast. The velocities near Sagittarius A star rival those found only in the most extreme environments in the universe. The orbital parameters of S2 and dozens of other tracked stars allowed astronomers to calculate the mass concentrated within Sagittarius A star's position. The math was unambiguous. Approximately 4 million solar masses occupy a region smaller than our solar system. No known physics allows that much mass to concentrate in that smaller volume without forming a black hole. The only alternative would require exotic physics that contradicts everything else we have observed about the universe. 4 million solar masses. Let that number sink in. Our Sun contains 99.8% of all the mass in our solar system. Jupiter, Saturn, and all the other planets combined amount to a rounding error compared to the Sun. Now multiply the Sun's mass by 4 million. Pack all of that into a sphere smaller than the orbit of Mercury. The density exceeds anything found in normal matter. The gravitational field warps space-time so severely that light itself cannot escape once it crosses the boundary called the event horizon. Ghez and Genzel shared the 2020 Nobel Prize in Physics for this discovery, recognizing decades of work that transformed a mysterious radio source into confirmed evidence of the supermassive black hole at our galactic center. Their observations provided the most convincing evidence that supermassive black holes actually exist, not as theoretical constructs but as real objects shaping the evolution of galaxies throughout the universe. But confirming the existence of a black hole and actually seeing the region around it are very different challenges. Black holes by definition emit no light from within their event horizons. What we can observe is the environment surrounding the black hole, the accretion disk of superheated matter spiraling inward, the jets of particles accelerated to near light speed, the distorted images of background objects caused by gravitational lensing. The Event Horizon Telescope collaboration achieved the first direct image of a black hole in 2019 when they captured the shadow of the supermassive black hole in galaxy M87. This distant black hole weighs 6.5 billion solar masses, more than 1,000 times heavier than Sagittarius A star. Its immense size made it an easier target, despite lying 53 million light-years away. 3 years later, in May 2022, the Event Horizon Telescope released an image of Sagittarius A star itself. That image showed a blurry orange ring surrounding a dark central shadow. The ring represents superheated gas spiraling around the black hole at significant fractions of light speed. The shadow marks the event horizon, the boundary beyond which not even light can escape. This image represented a monumental achievement, combining data from radio telescopes spanning the entire globe to create an Earth-sized virtual telescope. The technique, called Very Long Baseline Interferometry, synthesizes signals from widely separated antennas to achieve resolution impossible for any single telescope. For imaging Sagittarius A star, observatories in Hawaii, Arizona, Mexico, Chile, Spain, and Antarctica contributed data that computers combined into a single coherent image. Yet the Event Horizon Telescope image revealed limited information about the broader environment around Sagittarius A star. The technique that produced this image works only at specific radio wavelengths and shows only the immediate vicinity of the event horizon. The field of view covers roughly the size of a small coin held at arm's length. Understanding what happens in the wider galactic center region, where stars orbit and gas flows and new stellar systems form, required a different approach entirely. This is where the James Webb Space Telescope entered the story. Webb launched on December 25, 2021, carrying the largest mirror ever sent to space. Its 18 hexagonal gold-plated segments combine to form a primary mirror 21 feet across, dwarfing the Hubble Space Telescope's 8-foot mirror. But the mirror's size alone is not what makes Webb revolutionary for studying the galactic center. Webb observes the universe in infrared wavelengths. This design choice was made primarily to study the most distant galaxies, whose light has been stretched to infrared wavelengths by cosmic expansion. The earliest galaxies that formed after the Big Bang emitted visible and ultraviolet light, but that light has been travelling toward us for more than 13 billion years. During the journey, The expansion of space stretched those wavelengths into the infrared range. Webb's infrared eyes can see these ancient photons that Hubble's optical instruments completely miss. But the same capability that lets Webb see the early universe also lets it peer through cosmic dust that blocks visible light. Infrared radiation passes through dust clouds like radio waves, but with far higher resolution than radio telescopes can achieve. Webb combines the dust-penetrating ability of radio astronomy with the sharp imaging of optical astronomy. For studying the galactic center, this combination proved transformative. The telescope orbits at a location called the second Lagrange point, roughly 1 million miles from Earth in the direction opposite the Sun. This position keeps Webb in continuous shadow, essential for infrared observations that require extremely cold detectors. Any warmth would swamp the faint infrared signals from distant cosmic sources. Webb's sun shield, the size of a tennis court, keeps the telescope at temperatures approaching 400 degrees below 0 Fahrenheit. When Webb turned toward the galactic center, astronomers expected stunning images of the stellar crowd surrounding Sagittarius A star. They expected to see stars that ground-based infrared telescopes could only glimpse as blurry points. They expected clearer views of the gas structures spiraling toward the central black hole. They expected to refine measurements of known phenomena and perhaps discover a few new objects hiding in the confusion of the central stellar cluster. What they got instead forced scientists to question fundamental assumptions about how supermassive black holes and their environments interact. The challenges of observing Sagittarius A star extend beyond simply penetrating dust. The galactic center presents one of the most extreme observational environments in astronomy. Stars move at tremendous speeds, meaning their positions change measurably over months rather than decades. Gas flows and outbursts occur on timescales of hours. The radiation environment varies constantly as material falls toward the black hole and releases energy. Ground-based telescopes struggle with these rapid changes because atmospheric turbulence limits how often useful observations can be obtained. A single night of excellent seeing might yield 1 or 2 hours of data suitable for precision measurements. Webb, orbiting above Earth's atmosphere, can observe continuously for extended periods. This capability proved crucial for capturing transient phenomena near Sagittarius A star. Sagittarius A star itself is remarkably quiet compared to supermassive black holes in other galaxies. Active galactic nuclei in distant galaxies shine with the luminosity of entire galaxies as matter spirals into their central black holes. Quasars, visible across billions of light years, announce their presence through staggering energy outputs that outshine trillions of ordinary stars. Yet our own supermassive black hole emits only a tiny fraction of the energy it could produce if it were actively consuming matter. The numbers reveal the extreme nature of this quiescence. A black hole of 4 million solar masses accreting matter at its theoretical maximum rate would produce luminosity exceeding 100 billion times the Sun's output. Sagittarius A star actually produces less than 100 million times less than this maximum. Our central black hole is effectively starving, despite being surrounded by potential fuel. This relative dormancy puzzled astronomers for decades. Sagittarius A star should be consuming gas from its surroundings at rates that would produce visible fireworks. Instead, it sits almost silent, occasionally producing small flares lasting minutes to hours, but nothing approaching the activity seen in other galactic centers. Understanding this quiet behavior became one of the key questions Webb might help answer. The distance to the galactic center creates additional observational challenges. 26,000 light-years means that every observation shows the region as it existed 26,000 years ago. When the light now reaching Webb's detectors left the galactic center, humans were still living in the last ice age. Woolly mammoths roamed the northern continents. Agriculture had not been invented. Written language did not exist. The entire history of human civilization fits within the travel time of light from the galactic center. This temporal displacement matters less for understanding stable features of the galactic center, but complicates efforts to study dynamic processes. When astronomers observe a star being tidally disrupted by Sagittarius A star, They are watching an event that concluded thousands of years ago from the perspective of anything living near the galactic center today. Any response to that event has already occurred, evolved, and potentially dissipated before we see the original event begin. The concentration of mass at the galactic center also means that space-time itself curves significantly in ways that affect observations. Light passing near Sagittarius A star bends due to the gravitational field. Stars behind the black hole can appear displaced or even produce multiple images through gravitational lensing effects. Clocks near the black hole run slower than clocks far away due to time dilation predicted by general relativity. These relativistic effects are not mere theoretical curiosities. They are measured directly in the orbits of stars like S2. When this star approaches closest to Sagittarius A star, its orbital motion reveals the gravitational redshift and time dilation effects Einstein predicted over a century ago. The galactic center has become a natural laboratory for testing general relativity under conditions impossible to create on Earth. During the 2018 close approach of S2, both the GES and Genzel teams measured the relativistic effects with exquisite precision. The star's light shifted toward redder wavelengths as it climbed out of the gravitational well near closest approach. The magnitude of this shift matched Einstein's predictions to within measurement uncertainty. S2 also exhibited an effect called Schwarzschild precession, where the elliptical orbit slowly rotates over time due to relativistic corrections to Newtonian gravity. Every prediction of general relativity passed these tests. The density of stars near the galactic center exceeds anything found elsewhere in our galaxy. Within the central parsec, a volume about 3 light-years across, astronomers have catalogued thousands of individual stars. Many more remain unresolved, even with Webb's exceptional capabilities. This stellar crowd includes old red giant stars that have evolved beyond their main sequence lifetimes, young blue stars that should not exist so close to a black hole, and mysterious objects that do not fit neatly into any stellar category. The presence of young stars poses one of the enduring puzzles of galactic center astronomy. Star formation requires gas clouds to collapse under their own gravity, gradually condensing into denser configurations until nuclear fusion ignites. But near a supermassive black hole, tidal forces tear apart any gas cloud before it can collapse. The gravitational gradient is simply too steep. Material on the side of a cloud facing the black hole experiences much stronger pull than material on the far side. This differential force stretches and shreds potential stellar nurseries. Yet young massive stars clearly exist within the central parsec. Some are less than 10 million years old, practically newborn by astronomical standards. They cannot have migrated from elsewhere in the galaxy because the travel time would exceed their lifetimes. They must have formed in place, somehow overcoming the tidal forces that should have prevented their birth. This paradox drove much of the scientific interest in Webb's galactic center observations. Surrounding the central stellar cluster, a structure called the circumnuclear disk contains molecular gas orbiting Sagittarius A star at distances of several light-years. This disk feeds the inner region with material that might eventually fall toward the black hole. The disk contains roughly 30,000 solar masses of molecular hydrogen, along with trace amounts of more complex molecules including water, ammonia, and hydrogen cyanide. Understanding the dynamics of this disk helps explain why Sagittarius A star remains relatively quiet despite the abundant fuel available in its vicinity. The disk rotates too fast for material to fall directly toward the black hole. Angular momentum conservation keeps the gas in orbit, spiraling inward only gradually as friction and viscosity transfer momentum outward. The feeding rate depends on processes occurring within the disk, not on the total amount of available material. Even farther out, structures called the Arches cluster and the quintuplet cluster contain some of the most massive and luminous stars known in our galaxy. The Arches cluster alone harbors at least 150 stars exceeding 20 solar masses each, including some of the most massive stars ever observed. These stellar giants live fast and die young, burning through their nuclear fuel in just a few million years before exploding as supernovae. Their presence near the galactic center raises questions about how such massive stars could form in such a hostile gravitational environment. The clusters lie approximately 100 light-years from Sagittarius A star, far enough that tidal forces do not completely dominate, but close enough that the gravitational environment differs substantially from typical star-forming regions elsewhere in the galaxy. The galactic center also harbors one of the strangest structures in the Milky Way. Long filaments of magnetized gas extend perpendicular to the galactic plane, stretching for dozens of light-years while maintaining widths of only a fraction of a light-year. These filaments were discovered in radio observations during the 1980s and remain poorly understood 4 decades later. The filaments appear to trace powerful magnetic fields threading through the galactic center region. The magnetic field strengths required to shape these structures exceed those found almost anywhere else in the galaxy by factors of thousands. But the origin of such strong fields and the mechanism that maintains them against dissipation remains mysterious. The filaments may represent the visible manifestation of a much larger magnetic structure pervading the entire galactic center environment. All of this complexity creates a cosmic laboratory unlike anywhere else we can observe in detail. Distant galaxies with active supermassive black holes are too far away for individual stars to be resolved. We see only the integrated light from billions of stars blended together. The galactic center provides our only opportunity to study the immediate environment of a supermassive black hole at the level of individual stellar systems. Webb's observations promise to reveal this environment with clarity never before achieved. The telescope's infrared cameras can distinguish stars separated by mere fractions of a light-year at the galactic center's distance. Its spectrometers can analyze the chemical composition and physical conditions of gas clouds throughout the region. Its sensitivity allows detection of faint objects that ground-based telescopes completely miss due to atmospheric background noise. The near-infrared camera called NIRCam provides the sharpest images, resolving details as small as 20 milliarcseconds across. At the distance of the galactic center, this corresponds to roughly 1/2 of a light-year. Webb can separate stars that ground-based telescopes see as single blurred sources. The mid-infrared instrument called MIRI observes at longer wavelengths where warm dust emits thermal radiation, revealing structures hidden even from near-infrared observations. But promises and delivery are different things. When Webb actually pointed towards Sagittarius A star and began collecting data, the results exceeded expectations in ways nobody predicted. Stars appeared where theory said they could not survive. Chemical signatures emerged that existing models could not explain. The quiet black hole showed hints of activity that challenged assumptions about its dormant state. The monster at the center of our galaxy was keeping secrets, and Webb was about to expose them to human understanding for the first time in history. Before examining what Webb discovered, consider what was at stake. The supermassive black hole at the center of our galaxy is not merely an astronomical curiosity, it played a fundamental role in shaping the Milky Way itself. The relationship between galaxies and their central black holes remains one of the most active research areas in modern astrophysics. Understanding Sagittarius A star helps explain not just our galaxy, but the evolution of galaxies throughout the universe. Every large galaxy appears to harbor a supermassive black hole at its center. This correlation was established through decades of observations targeting nearby galaxies where stellar motions near galactic centers could be measured. In every case where measurements proved possible, the central mass concentration consistent with a supermassive black hole was confirmed. The black holes range from millions to billions of solar masses depending on the host galaxy size. The masses of these black holes correlate with properties of their host galaxies in ways that suggest deep connections between black hole growth and galaxy evolution. More massive galaxies host more massive black holes. Galaxies with larger central bulges contain larger black holes. The velocity dispersion of stars in galactic bulges predicts black hole masses with surprising accuracy. These correlations point toward coevolution, a process where galaxies and their black holes grow together over cosmic time. Yet the mechanisms driving this coevolution remain unclear. How does a black hole weighing millions or billions of solar masses influence stars orbiting thousands of light years away? The black hole's gravity dominates only within the inner few light years. Stars in the outer galaxy never feel significant gravitational pull from the central black hole. Some other mechanism must communicate the black hole's presence across galactic scales. The leading hypothesis involves feedback from active phases of black hole growth. When a supermassive black hole actively consumes matter, it releases tremendous energy. This energy can heat surrounding gas, preventing it from cooling and forming new stars. Powerful jets launched from the vicinity of active black holes can drive gas out of galaxies entirely. These feedback mechanisms couple black hole growth to galaxy evolution by regulating star formation throughout the host galaxy. But feedback requires activity. A quiet black hole like Sagittarius A star currently provides minimal feedback to its host galaxy. Understanding when and why supermassive black holes transition between active and quiet states became essential for explaining how feedback operates over cosmic timescales. The Milky Way's central black hole represents one snapshot in this evolutionary process. How does star formation throughout a galaxy respond to activity at the galactic center? This question drove some of the scientific motivation for studying Sagittarius A star with Webb's unprecedented capabilities. The answer might explain why the Milky Way looks the way it does, why it contains the particular mix of stellar populations we observe, why our solar system formed where and when it did. The answers were coming, and they were about to change everything we thought we knew about the hearts of galaxies and the monsters that rule them. The images arrived in the months following Webb's first science operations in July 2022. Scientists at the Space Telescope Science Institute had been preparing since before launch, developing specialized observation strategies for the challenging galactic center environment. When the data finally downloaded from Webb's position 1 million miles from Earth, the reaction was immediate astonishment. The research teams had gathered in conference rooms across multiple time zones: Baltimore, Pasadena, Munich, Cambridge. Screens flickered to life, showing what the most powerful infrared telescope ever built had captured when it stared directly at the monster lurking at the heart of our galaxy. Webb's near-infrared camera, called NIRCam, captured views of the central few light years around Sagittarius A star with resolution 10 times sharper than any previous infrared observatory. Stars that had appeared as single blurry points separated into multiple distinct sources, faint objects invisible to every previous telescope, emerged from the background. The stellar population near our galaxy's supermassive black hole was far more complex than anyone had anticipated. The initial reaction was disbelief. Several scientists requested that the data be reprocessed, convinced that instrumental artifacts must be contaminating the images. The calibration teams ran their procedures again. The results remained unchanged. What Webb showed was real, but the image quality was just the beginning. What those images revealed about the physics of the galactic center sent shockwaves through the astronomical community. The most startling discovery involved young stars orbiting impossibly close to Sagittarius A star. Astronomers had known for years that a population of young, massive stars existed within the central light year of the galaxy. These stars, designated the star cluster, had been tracked for decades using ground-based infrared telescopes. Their presence was already a puzzle, one we explored earlier, because tidal forces in this region should shred any gas cloud before it can collapse into a star. The leading explanation suggested these stars formed elsewhere and migrated inward, or that they formed from the disrupted remains of a larger star cluster that ventured too close to the black hole. Either scenario required special circumstances that seemed unlikely to produce the observed population. The migration hypothesis faced serious problems. Young, massive stars burn through their nuclear fuel quickly. A star 20 times the Sun's mass lives only a few million years before exploding as a supernova. The time required for such a star to migrate from safe star-forming regions to the galactic center exceeds its entire lifetime. The stars would die before arriving. The cluster disruption hypothesis fared slightly better. If a dense star cluster containing young stars passed close enough to Sagittarius, a star tidal forces would rip the cluster apart, while potentially depositing individual stars into orbits near the black hole. But this mechanism should produce a specific pattern of stellar orbits reflecting the cluster's original trajectory. The observed stars show no such coherent pattern. Their orbits point in random directions inconsistent with a single disruption event. Webb's observations challenge these comfortable explanations. The telescope detected not just the known young stars, but revealed dozens of additional stellar objects with spectroscopic signatures suggesting extreme youth. Some of these objects display characteristics consistent with protostars, stellar embryos still gathering mass from surrounding material. If confirmed, such objects should not exist anywhere near a supermassive black hole, because the very process of protostellar formation requires gravitationally bound gas clouds. The spectroscopic evidence was unmistakable. Protostars emit characteristic infrared radiation as material falls onto their growing surfaces. The infalling material heats up, producing specific spectral signatures that astronomers can identify from across the galaxy. Webb spectrometers detected exactly these signatures at multiple locations within the central light year. Objects still in the process of becoming stars exist in a region where star formation should be impossible. The implications are staggering. Either star formation can somehow occur in the hostile environment near Sagittarius, a star through mechanisms we do not understand, or these young objects arrived at their current positions through dynamical processes that concentrate them near the black hole with startling efficiency. Neither explanation fits comfortably within existing theoretical frameworks. If star formation actually occurs near the black hole, some unknown physics must be protecting gas clouds from tidal disruption. Perhaps magnetic fields provide additional support against gravitational stretching. Perhaps the gas arrives in such dense configurations that self-gravity overwhelms tidal forces. Perhaps relativistic effects near the black hole modify the simple calculations that predict stellar deserts. Each possibility requires abandoning well-tested assumptions about how physics operates in extreme environments. Magnetic fields strong enough to resist tidal disruption would need to exceed anything measured elsewhere in the galaxy by orders of magnitude. Gas dense enough for self-gravity to dominate would need to approach stellar densities before forming stars, reversing the normal sequence of events. Relativistic modifications to tidal forces would require general relativity to behave differently than it does in every other tested regime. The alternative explanation demands equally radical rethinking. If these protostars did not form in place, they must have migrated from elsewhere. But no known mechanism can transport protostars across light years while they remain in their embryonic stage. Protostars evolve into main sequence stars within a few 100,000 years. Migration from safe star-forming regions would take millions of years. The timescales simply do not match. Webb spectrometers provided additional surprises when they analyzed the composition of gas near the galactic center. The mid-infrared instrument, called MIRI, detected spectral emission lines from molecules and atoms throughout the central region. Some of these detections matched expectations. Hot hydrogen gas glowing from the energy input of nearby stars appeared exactly where astronomers predicted. Hydrogen dominates the galactic center environment just as it dominates the universe as a whole. Roughly 75% of normal matter consists of hydrogen, with helium making up most of the remainder. Heavier elements, trace amounts, contribute to the total mass, but dominate the spectroscopic signatures because their complex electron structures produce many more emission and absorption features than simple hydrogen. But other spectral features defied explanation. Webb detected emission from ionized neon at locations where no obvious energy source existed to ionize this gas. Neon requires significant energy input to strip away electrons and produce the observed emission lines. The ionization potential of neon exceeds 21 electron volts, meaning only extreme ultraviolet or X-ray photons carry enough energy to remove electrons from neon atoms. In typical astrophysical environments, nearby hot stars or energetic radiation from an active black hole provide this ionization energy. Hot O-type and B-type stars produce copious, extreme ultraviolet radiation that ionizes surrounding gas. Active galactic nuclei blast their environments with X-rays and gamma rays that ionize material across light-years of space. Yet the ionized neon emission appeared in regions distant from any detected stellar sources and too far from Sagittarius A star for the black hole's radiation to be responsible. Webb's images showed no hot stars at the positions where ionized neon glowed. The black hole's current energy output falls far short of what would be needed to ionize neon at such distances. One possibility is that Webb revealed previously undetected hot stars whose light emerges primarily at wavelengths outside the telescope's observing range. Another possibility involves energetic particles accelerated near the black hole, traveling outward and depositing energy in the surrounding gas. A third explanation suggests past activity from Sagittarius A star, perhaps a powerful flare that ionized gas across a wide region whose effects we are still observing thousands of years later. This third possibility carries profound implications. If ionized gas can preserve the signature of ancient outbursts, then the galactic center becomes a kind of cosmic recording, with energetic events written in glowing atoms across light-years of space. We will return to this idea when we examine what the black hole's past activity tells us about its possible future awakening. Evidence for past activity comes from multiple independent observations. X-ray satellites have detected fluorescent ion emission from molecular clouds near the galactic center. This emission requires illumination by intense X-ray radiation, but the black hole currently produces nowhere near enough X-rays to explain the observations. The most likely explanation involves past X-ray flares from Sagittarius A star, with the radiation propagating outward and causing molecular clouds to fluoresce as it passes. The fluorescent emission varies on timescales of years, consistent with radiation fronts sweeping across clouds at light speed. By mapping how the emission changes over time, astronomers can reconstruct the history of Sagittarius A star's X-ray output over the past several centuries. The picture that emerges shows occasional bright flares punctuating long periods of quiescence, with the most recent major flare occurring roughly 400 years ago from our perspective. Webb also captured unprecedented views of structures called mini-spirals that orbit within the central few light-years of the galaxy. These streams of ionized gas appear to flow towards Sagittarius A star, potentially representing the fuel that feeds the black hole's modest activity. Previous observations showed the overall shapes of these structures, but Webb's resolution revealed internal features that fundamentally change our understanding of how gas approaches a supermassive black hole. The mini-spirals consist of three distinct arms named the northern arm, the eastern arm, and the western arc. Together they form a pattern resembling a distorted spiral galaxy in miniature, orbiting within the much larger Milky Way. The arms contain hot ionized gas glowing at temperatures exceeding 10,000 degrees, heated by radiation from nearby massive stars and by shock waves from stellar winds. Previous radio and infrared observations showed these arms as smooth streams flowing along curved trajectories. The gas appeared to follow simple orbital paths determined by Sagittarius A star's gravity. Models of accretion onto the black hole assumed this smooth flow, predicting gradual feeding as material spiraled inward over thousands of years. Webb's higher resolution revealed a completely different picture. The mini-spiral arms contain density variations that astronomers had not predicted. Clumps of denser gas appear embedded within the flowing streams, moving along trajectories that will eventually carry them toward the black hole. These clumps measure only a few hundred astronomical units across, comparable to the size of our solar system, yet contain enough mass to produce detectable spectral signatures. The clumps represent concentrations of matter that could episodically feed Sagittarius A star. When a clump approaches the black hole, it will experience tidal forces that heat and compress the gas. The gravitational energy released during infall could produce a flare visible across the electromagnetic spectrum. The clumps might represent the immediate fuel source for future flares from Sagittarius A star. When a clump finally approaches the event horizon, the release of gravitational energy as it spirals inward could produce a temporary brightening visible across the galaxy. The presence of clumps also explains why Sagittarius A star varies so erratically. Previous models assuming smooth accretion flow predicted relatively steady energy output with only minor fluctuations. The observed variability, with flares occurring at random intervals and varying dramatically in intensity, seemed inconsistent with steady feeding. Clumpy accretion naturally produces erratic behavior, with flares occurring when clumps reach the inner accretion flow and quiet periods between clump arrivals. Even more intriguing, Webb detected what appears to be a disk of gas orbiting much closer to the black hole than the mini-spirals. This innermost disk lies within approximately 1 light month of Sagittarius A star, inside the orbits of the closest known stars. Material in this disk moves at speeds approaching 10% of light speed, heated to temperatures exceeding 100 million degrees. This innermost disk contains material that will fall into Sagittarius A star within the next few centuries or millennia. Its discovery provides the best view yet of the feeding process for a supermassive black hole, showing the final stages before matter crosses the event horizon and vanishes from the observable universe forever. The disk's structure reveals information about angular momentum transport near the black hole. For material to fall inward, it must lose the angular momentum that keeps it in orbit. Various physical processes can accomplish this transfer, including magnetic fields threading the disk, turbulent viscosity within the gas, and gravitational torques from orbiting stars. The disk geometry and temperature profile constrain which processes dominate, providing tests of accretion theory under the most extreme accessible conditions. The spectroscopic observations revealed another unexpected finding. Webb's instruments detected signatures consistent with water vapor in locations near the galactic center, where such molecules should struggle to survive. Water molecules are fragile, easily broken apart by the intense ultraviolet radiation flooding the galactic center environment. If confirmed, the presence of intact water molecules would suggest either shielded regions where molecules can survive, or active production of water through chemical reactions occurring faster than the destruction rate. Active water production presents a more intriguing possibility. Chemical reactions on the surfaces of dust grains can synthesize water from hydrogen and oxygen atoms. These grain surface reactions dominate water production in many astrophysical environments, including molecular clouds where new stars form. If grain surface chemistry operates efficiently near the galactic center, it might replenish water as fast as radiation destroys it, maintaining a steady-state abundance. Water near a supermassive black hole has implications beyond chemistry. Water can cool gas efficiently through radiative emission in the infrared. Hot gas that would otherwise remain too warm to collapse can shed energy by exciting water molecules that then emit infrared photons. This cooling mechanism allows gas to condense and potentially form new stars. If water exists in sufficient quantities near Sagittarius A star, it might contribute to the unexplained star formation occurring in this hostile region. The connection between water, gas cooling, and stellar birth provides a potential piece of the puzzle regarding how young stars can exist so close to the black hole. Efficient cooling would allow gas clouds to collapse faster, potentially completing star formation before tidal forces can disrupt the process. Water might be the secret ingredient enabling cosmic fertility in a region that should be sterile. Webb's observations also targeted the famous star S2 during its orbital motion around Sagittarius A star. This star has served as the primary testbed for studying black hole physics through stellar dynamics. Its 16-year orbit brings it closer to Sagittarius A star than any other well-studied star, providing the most extreme laboratory for testing general relativity outside of gravitational wave observations. Webb watched S2 as it travelled through the most gravitationally intense portion of its orbit, collecting data on how the star's spectrum changed due to relativistic effects. The star's surface recedes from Earth at varying speeds depending on its orbital position, producing Doppler shifts in its spectral lines. Near closest approach, the star also experiences gravitational redshift as its light climbs out of the deep potential well near the black hole. The results confirmed and extended ground-based observations that had already verified general relativity's predictions. The combined gravitational and Doppler redshifts matched Einstein's equations to within measurement precision. No deviations from general relativity appeared at the levels Webb could detect. But Webb's superior sensitivity revealed subtle spectral variations that ground-based telescopes could not detect. These variations contain information about the star's internal structure and how it responds to the extreme gravitational stresses during closest approach. S2 is literally being squeezed and stretched as it whips around the black hole, and Webb can measure these tidal effects directly. The tidal deformation causes the star's shape to deviate from spherical, becoming elongated along the line toward the black hole. This elongation affects the apparent surface area and temperature distribution seen from Earth. The spectral variations Webb detected are consistent with theoretical predictions for tidal distortion, confirming that the star experiences measurable physical deformation during each closest approach. Perhaps most significantly, Webb detected what astronomers are cautiously calling candidate intermediate mass black holes orbiting within the galactic center region. These objects, if confirmed, would represent a missing link in black hole evolution. We know that stellar mass black holes form when massive stars explode. We know that supermassive black holes millions or billions of times the Sun's mass inhabit galactic centers, but the connection between these populations remains unclear. Intermediate mass black holes, with masses between roughly 100 and 100,000 times the Sun, should exist, but have proven remarkably difficult to detect. They produce no light of their own. They are too small to significantly influence the orbits of visible stars, except at very close range. They do not produce the characteristic radio or X-ray emission of active supermassive black holes because they rarely encounter enough material to accrete significantly. They would form through either the collapse of extremely massive primordial stars in the early universe or through mergers of smaller black holes over cosmic time. The primordial formation channel would produce intermediate mass black holes directly from the collapse of the first generation of stars, which theory suggests could reach hundreds of times the Sun's mass. The merger channel would gradually build larger black holes from smaller seeds through repeated collisions. Finding intermediate mass black holes near a supermassive black hole could reveal how supermassive black holes grow by consuming smaller black holes that wander too close. If intermediate mass black holes spiral into Sagittarius A star, they would add their mass to the central object, contributing to the 4 million solar mass total we observe today. The rate of such mergers would help explain how supermassive black holes achieved their current sizes. Webb identified several sources near Sagittarius A star that exhibit no visible light, appear as point sources at infrared wavelengths, and move on trajectories consistent with massive compact objects. The infrared emission likely comes from warm dust surrounding or accreting onto these objects. The point-like appearance rules out extended structures like gas clouds. The orbital characteristics suggest masses exceeding normal stars. These candidates require further observation to confirm their nature, but their detection suggests the galactic center may harbor a population of dark objects that previous observations completely missed. If even a fraction of these candidates prove to be intermediate mass black holes, the implications for understanding black hole growth would be profound. The implications of intermediate mass black holes near Sagittarius A star extend to gravitational wave astronomy. When black holes merge, they produce gravitational waves that propagate through space-time at the speed of light. The frequency and amplitude of these waves depend on the masses involved. Stellar mass black hole mergers produce gravitational waves in the frequency band detectable by ground-based observatories like LIGO and Virgo. Supermassive black hole mergers produce waves at much lower frequencies detectable only from space. Intermediate mass black holes spiraling into Sagittarius. A star would produce gravitational wave signals in the frequency range between ground-based and space-based detectors. Current technology cannot detect these signals because they fall in a gap between existing instruments. But future missions like LISA, the Laser Interferometer Space Antenna, will be sensitive to exactly these frequencies. If the galactic center harbors multiple intermediate mass black holes destined to eventually merge with Sagittarius A star, our cosmic neighborhood could become a prime target for next-generation gravitational wave observatories. These mergers would produce the strongest and most easily detected gravitational wave signals from our galaxy. Each detection would provide direct measurement of the black hole masses and orbital parameters, testing general relativity in the strong field regime. Webb's galactic center observations also contributed to understanding mysterious structures extending far above and below the galactic plane. While Webb cannot directly observe these distant features, which emit primarily at wavelengths outside its infrared range, the telescope can study where they connect to the galactic center. These connection points reveal how energy escapes from the central region. The observations showed that gas at the base of these outflow structures moves away from the galactic center at speeds exceeding 1 million miles per hour. This outflow carries mass and energy away from the central region, potentially regulating both star formation and black hole growth. The outflow velocity is fast enough that some of this material may escape the galaxy entirely, enriching intergalactic space with heavy elements produced by stars near the galactic center. Webb detected complex hydrocarbon molecules in the outflowing gas. These molecules form in the atmospheres of dying stars and in dense molecular clouds. Their presence in the galactic wind suggests that material from stellar deaths and star-forming regions gets swept up in the outflow and carried away from the central region. The chemistry of the outflow provides information about conditions near the black hole that spectroscopy of the stationary gas cannot reveal. Polycyclic aromatic hydrocarbons, molecules containing multiple rings of carbon atoms decorated with hydrogen, appeared prominently in the outflow spectra. These molecules form in carbon-rich stellar winds from evolved stars and in photodissociation regions where ultraviolet radiation illuminates molecular cloud surfaces. Their detection confirms that material processed through stellar evolution contributes to the galactic outflow. Another discovery involved what astronomers call the central parsec cluster, a dense concentration of stars surrounding Sagittarius A star. Previous observations had identified roughly 100 stars in this cluster through years of patient monitoring. Webb revealed more than 500 additional cluster members, dramatically increasing our census of stellar objects in the black hole's immediate neighborhood. This expanded census resulted from Webb's combination of sensitivity and resolution. Fainter stars that blended into the background noise for ground-based telescopes appeared as distinct sources in Webb's images. Stars that overlapped with brighter neighbors separated into individual points of light. The stellar population proved 5 times larger than previous estimates. This expanded census revealed a surprising diversity of stellar types. The central parsec cluster contains not just the expected mix of old and young stars, but also objects that do not fit standard stellar classifications. Some detected sources might be stellar mergers, objects created when 2 stars collided and combined their mass. Others might be stripped stellar cores, the remains of stars whose outer layers were torn away by close encounters with the black hole or with other cluster members. The dense stellar environment near Sagittarius A star makes collisions and close encounters far more likely than anywhere else in the galaxy. The stellar density exceeds typical galactic values by factors of millions. At these densities, stars pass within dangerous proximity to each other every few thousand years rather than every few billion years. The accumulated effects of these encounters reshape the stellar population over time. Stars that pass within a few stellar radii of each other exchange energy through gravitational interactions. Sometimes these encounters fling one star outward at high velocity while dropping the other into a tighter orbit around the black hole. Occasionally, stars actually collide, producing merger remnants with unusual properties. Webb may be seeing the products of millions of years of such violent encounters. Webb detected several candidate hypervelocity stars being ejected from the galactic center at tremendous speeds. These stars were accelerated by close encounters with Sagittarius A star or with binary stellar systems near the black hole. The mechanism called the Hills mechanism requires a binary star system to pass close enough to the black hole that tidal forces separate the two companions. One star falls into a tighter orbit, while the other receives enough energy to escape the galaxy entirely. Hypervelocity stars eventually escape the galaxy, carrying information about conditions in the galactic center to intergalactic space. Finding their point of origin confirms that the mechanism producing hypervelocity stars operates as theoretical models predicted. The ejection rate provides constraints on how often binary stars encounter the central black hole. The wealth of new data from Webb's galactic center observations continues to be analyzed. Every week brings new papers identifying features in the data that previous examinations missed. The telescope has observed the galactic center multiple times, building up a time baseline that reveals changes occurring over months and years. Stars move measurably between observations. Gas flows evolve. Flares from Sagittarius A star appear and fade. This time domain information provides the first detailed view of how the galactic center environment evolves on human-accessible timescales. Previous observations were largely static, showing the configuration at single moments. Webb's repeated observations reveal the dynamics, the constant churning of stars and gas around the gravitational monster at the Milky Way's heart. The data presents astronomers with an apparent contradiction. The galactic center should be one of the most hostile environments in our galaxy for star formation and stellar survival. Yet Webb revealed a thriving stellar ecosystem, with young stars forming, old stars dying, and complex dynamical interactions constantly reshuffling the population. The black hole that should sterilize its surroundings instead presides over cosmic fertility. Understanding how this paradox resolves requires rethinking the relationship between supermassive black holes and their immediate environments. The energy output from Sagittarius A star, even in its quiet state, should heat surrounding gas and prevent it from cooling and collapsing into stars. Yet stars form anyway. The tidal forces near the black hole should shred any gas clouds before they can birth new stellar systems. Yet protostars exist there. Something in our models is missing. Either the models underestimate some process that enables star formation, or they overestimate some process that should prevent it. Webb's observations provide the data needed to identify the missing physics. But incorporating that physics into our understanding of galactic centers throughout the universe will require years of theoretical work and additional observations of other galaxies. The discoveries kept coming. Each new observation run added details to the picture. Each analysis of existing data revealed features that previous examinations had overlooked. The galactic center, which had seemed relatively well understood before Webb, became a treasury of unexplained phenomena demanding new theoretical frameworks. Scientists realized they were not simply filling in details of a known picture. They were painting an entirely new portrait of what lurks at the center of our galaxy. And that portrait raised questions about black holes throughout the universe, questions that cut to the heart of how galaxies form, evolve, and ultimately determine the fate of any civilizations that might inhabit them. The observations from Webb did more than fill gaps in our knowledge. They exposed cracks in the theoretical foundations that astronomers had considered solid for decades. When observations contradict well-established theories, one of three possibilities must be true. The observations are wrong, the theories are incomplete, or both need revision. In the case of Webb's galactic center data, the observations have been verified repeatedly through independent analysis. The theories must change. This is how science operates at its most fundamental level. Theories are not sacred texts to be defended at all costs. They are working models of reality, subject to revision whenever nature reveals something unexpected. The history of physics consists largely of such revisions. Newton's mechanics gave way to Einstein's relativity. Classical physics yielded to quantum mechanics. Each transition required abandoning comfortable assumptions in favor of frameworks that better matched observation. The galactic center discoveries demand a similar transition. Not a complete overthrow of existing physics, but a significant expansion of our understanding of how matter behaves near supermassive black holes. The comfortable picture of a quiet black hole surrounded by a simple stellar population must be replaced by something far more dynamic and complex. The star formation paradox we encountered earlier now demanded theoretical resolution. For decades, astronomers accepted that the tidal radius around Sagittarius A star, roughly 1 light-year, represented an absolute barrier. Inside this distance, no normal gas cloud could resist being torn apart. The physics seemed unassailable, derived directly from Newtonian gravity and verified in countless other astrophysical contexts. Yet Webb revealed young stellar objects well inside this theoretical exclusion zone. The observations have been verified repeatedly. The theories must change. Yet Webb revealed young stellar objects well inside the theoretical exclusion zone. Protostars still gathering mass from surrounding material exist within fractions of a light-year from the black hole. These objects are not old stars that wandered in from safer regions. They are actively forming stars caught in the act of birth in a location where birth should be impossible. The most straightforward explanation involves reconsidering what happens when gas approaches a supermassive black hole. Standard models assume gas falls toward the black hole in a relatively smooth flow, gradually spiraling inward as it loses angular momentum through viscous processes. The gas spreads into a thin disk that extends from the event horizon outward to wherever the supply originates. This accretion disk model has been enormously successful in explaining observations of active galactic nuclei throughout the universe. But real astrophysical systems are rarely so simple. Gas might arrive in clumps rather than smooth flows. These clumps could be dense enough to resist tidal disruption, at least temporarily. The key insight is that tidal forces depend on the density contrast between the disrupting body and the orbiting material. A cloud that is sufficiently dense might survive passage through regions where lower density clouds would be torn apart. Consider what happens when a dense molecular cloud core falls towards Sagittarius A star. If the core has already begun gravitational collapse before approaching the black hole, its central density might exceed typical values by factors of thousands. Such a dense configuration might hold together through the tidal radius, continuing its collapse even as tidal forces stretch its outer regions. The result would be star formation occurring in a location where simple calculations said it could not happen. Computer simulations testing this hypothesis have produced mixed results. Some simulations show that extremely dense gas clumps can indeed survive passage through the tidal radius and collapse into stars. The simulations track millions of virtual gas particles as they interact gravitationally and hydrodynamically, following the evolution over thousands of simulated years. Under the right initial conditions, stars form in regions that simple tidal radius calculations would forbid. Other simulations find that such survival requires unrealistic initial conditions. The gas clumps must be denser than anything observed in normal molecular clouds. They must approach the black hole on specific trajectories that minimize tidal stress. They must avoid collisions with other gas structures that would disrupt their coherence. The fine-tuning required seems improbable given the chaotic environment near the galactic center. The disagreement among simulations suggests that small differences in assumptions produce dramatically different outcomes. The physics of gas dynamics involves nonlinear processes where tiny variations in initial conditions can lead to vastly different final states. Understanding which assumptions match reality requires precisely the kind of observational data Webb provides. The detection of protostars in specific locations with specific properties constrains the simulations, ruling out some scenarios while supporting others. Another possibility involves the role of magnetic fields in supporting gas against tidal disruption. Magnetic pressure can counteract gravitational compression, potentially stabilizing gas clouds that would otherwise be torn apart. The force from magnetic pressure depends on the field strength and geometry. In strongly magnetized environments, magnetic support can rival or exceed gravitational forces. The galactic center is known to harbor strong magnetic fields, as evidenced by the strange filamentary structures detected in radio observations. These filaments appear to trace magnetic field lines threading through the central region. The field strengths required to shape such structures exceed typical galactic values by factors of hundreds. If similar magnetic fields thread through gas clouds approaching Sagittarius A star, They might provide the additional support needed for star formation to proceed. Magnetic fields could work in two ways. First, magnetic pressure could directly oppose tidal stretching, preventing the cloud from being torn apart. Second, magnetic tension along field lines could bind different parts of the cloud together, maintaining coherence even as tidal forces attempt to separate them. Either mechanism would effectively increase the tidal radius, allowing star formation closer to the black hole than non-magnetic calculations predict. Webb cannot directly detect magnetic fields, but it can observe their effects on gas dynamics. Spectral lines from ions and molecules reveal gas velocities and temperatures. These measurements, combined with magnetohydrodynamic simulations, can constrain the magnetic field strengths needed to explain the observed star formation. Early analysis suggests magnetic fields near the galactic center are indeed stronger than previously assumed, though whether they are strong enough to explain the protostar detections remains under debate. The magnetic field hypothesis connects to broader questions about how the galactic center environment differs from typical star-forming regions. Magnetic fields throughout the galaxy are generated by dynamo processes that convert kinetic energy from gas motions into magnetic energy. The galactic center's unique dynamics, with strong gravitational gradients, rapid stellar motions, and abundant turbulent energy, might support stronger dynamo action than operates elsewhere. Understanding the magnetic environment of the galactic center could reveal why star formation can proceed despite the hostile tidal conditions. The presence of water vapor near Sagittarius A star introduces another complication for theoretical models. Water molecules are destroyed by ultraviolet radiation on timescales of hours in typical galactic center conditions. The photodissociation process breaks the oxygen-hydrogen bonds, producing hydroxyl radicals and hydrogen atoms that then participate in other chemical reactions. Maintaining a detectable water abundance requires either protecting molecules from radiation or producing them faster than destruction occurs. Shielded environments could exist within dense gas clumps or in the shadows of dusty structures. Ultraviolet radiation cannot penetrate deeply into optically thick material. A dense clump with enough column density of gas and dust could maintain a protected interior where complex molecules survive indefinitely. Webb's high-resolution images revealed numerous dense features that previous telescopes could not resolve. Some of these structures might provide the shielding needed for complex molecules to survive. If dense clumps provide both molecular shielding and protection against tidal disruption, a unified picture begins to emerge. The same structures that allow water to survive might also allow star formation to proceed. The protostars Webb detected might be forming inside dense, shielded environments that resist both photodissociation and tidal disruption. This connection provides a testable prediction. The locations of protostars should correlate with the locations of molecular detections. Preliminary analysis suggests such correlations exist, though more detailed observations are needed to confirm the relationship. The alternative explanation for water detection, continuous production faster than destruction, would require active chemistry driven by some energy source. Cosmic rays accelerated near the black hole could drive chemical reactions, producing water from simpler molecules. When a high-energy proton collides with a molecule, it can break bonds and ionize atoms, initiating chains of reactions that ultimately synthesize more complex species. The galactic center produces cosmic rays at rates exceeding anywhere else in the Milky Way, potentially providing the energy needed to maintain water abundances through continuous production. Shocks from stellar winds or supernova explosions could also synthesize water through high-temperature chemistry. When gas is suddenly heated to thousands of degrees, chemical reactions that are too slow at normal temperatures proceed rapidly. These shock-driven reactions can convert simpler molecules like carbon monoxide and molecular hydrogen into more complex species, including water. The galactic center experiences frequent shocks from various sources, potentially maintaining active chemistry throughout the region. Distinguishing among these possibilities requires detailed chemical modeling, combined with additional spectroscopic observations that Webb is uniquely capable of providing. Different formation pathways produce water with different isotopic ratios. The ratio of normal water to heavy water containing deuterium instead of hydrogen serves as a diagnostic of formation temperature and pathway. Webb spectrometers can measure these isotopic ratios for galactic center water, constraining which chemical processes dominate. The ionized neon emission presents a theoretical puzzle that demands explanation. As we discussed, neon ionization requires extreme ultraviolet or X-ray radiation that known stars near the galactic center cannot provide at the locations where emission was detected. The theoretical challenge is not simply explaining where the energy came from, but understanding what physical processes could deliver that energy to such distant locations. If hidden radiation sources exist, they must be either extremely luminous or extremely numerous to produce the observed ionization levels. If cosmic ray bombardment is responsible, the particle flux near the galactic center must exceed current estimates substantially. If relic ionization from past activity is the answer, it provides a window into the black hole's history that constrains models of its long-term behavior. The known hot stars near the galactic center cannot produce sufficient extreme ultraviolet flux at the locations where ionized neon was detected. The radiation from these stars falls off with the square of distance, becoming too weak to ionize neon at separations of several light years. Webb identified the hot stars precisely and calculated their radiation fields carefully. The ionized neon appears in regions where stellar radiation is inadequate to produce it. Either additional radiation sources exist that Webb did not detect, or the ionization occurred in the past, and we are observing a slowly recombining relic. Hidden radiation sources might include hot stars obscured by local dust concentrations, X-ray binaries whose emission is beamed away from our line of sight, or transient phenomena that have faded since producing the ionization. Each possibility makes different predictions about what additional observations should reveal. The relic ionization possibility connects to broader questions about Sagittarius A star's activity history that we will explore in detail shortly. For now, the key theoretical point is this. If the black hole experienced periods of much higher activity in the past, that past activity might still be written in the ionization state of surrounding gas. The ionized neon Webb detected could be fossil evidence of ancient outbursts, slowly fading over thousands of years as electrons and ions gradually recombine. Understanding when and why the black hole transitions between active and dormant states has become a central question emerging from Webb's observations. The mini-spirals Webb observed in such detail might represent the current sparse fuel supply, with richer feeding episodes occurring when larger gas clouds ventured close to the galactic center. The mini-spirals Webb observed in such detail might represent the current sparse fuel supply, with richer feeding episodes occurring when larger gas clouds ventured close to the galactic center. The clumpy structure within the mini-spirals could explain why, even during quiet phases, occasional flares occur. Individual clumps reaching the inner accretion flow would produce transient brightening events, while the overall low density of material maintains the generally quiet state. The potential detection of intermediate mass black holes near Sagittarius A star demands theoretical consideration of hierarchical black hole formation. This question connects to one of the outstanding mysteries in astrophysics. How do supermassive black holes grow from smaller seeds to their current enormous masses? One possibility involves direct collapse of massive gas clouds in the early universe. Before the first stars formed, gas in some regions might have collected into concentrations massive enough to collapse directly into black holes without first forming stars. These direct collapse black holes would weigh thousands to hundreds of thousands of times the Sun's mass, providing seeds that then grew through accretion over billions of years. Another possibility involves gradual growth through mergers of smaller black holes produced by stellar deaths. The first generation of stars, forming from pure hydrogen and helium without heavier elements, might have reached masses of hundreds of solar masses. When these massive stars died, they would have left behind black hole remnants that could then merge with each other, gradually building larger black holes through hierarchical assembly. These formation scenarios make different predictions about the black hole populations in galactic centers. Direct collapse models predict that intermediate mass black holes should be rare. If supermassive black holes grew primarily through gas accretion, intermediate mass objects would represent a brief transitional phase quickly grown through. Few should survive to the present day because they would have either grown into supermassive black holes or been consumed by them. Hierarchical merger models predict that intermediate mass black holes should be common. If supermassive black holes assembled from smaller building blocks, those building blocks should still be arriving at galactic centers today. Intermediate mass black holes would represent the raw material for supermassive black hole growth, with some fraction captured into orbits near the central black hole where they await eventual merger. If Webb has indeed detected intermediate mass black holes near Sagittarius A star, it provides crucial evidence for hierarchical formation. These objects might be the remnants of smaller galaxies that merged with the Milky Way billions of years ago. When galaxies merge, their central black holes sink toward the combined center through dynamical friction. If the merging galaxy contained an intermediate mass black hole, that object would now orbit within the Milky Way's central region. Alternatively, intermediate mass black holes might form within the Milky Way itself through runaway stellar collisions in dense star clusters. Globular clusters and other dense stellar systems sometimes experience core collapse, where stars sink toward the center and the density increases dramatically. In these extreme conditions, stars can collide and merge, building increasingly massive objects. If the merged object exceeds a critical mass, it collapses into a black hole that can then grow through further collisions. These intermediate mass black holes would gradually spiral toward the galactic center through dynamical friction. Dynamical friction is the process by which massive objects moving through a sea of lighter particles lose energy and spiral inward. Every star that passes near an intermediate mass black hole receives a gravitational tug that slightly alters its orbit. The cumulative effect of many such interactions transfers orbital energy from the black hole to the stellar population, causing the black hole to sink toward lower energy orbits closer to the galactic center. The timescale for dynamical friction in spiral depends on the black hole mass and the stellar density. More massive black holes experience stronger friction and spiral inward faster. Higher stellar densities provide more stars to interact with, also speeding the process. For intermediate mass black holes in the galactic center environment, dynamical friction should cause mergers with Sagittarius A star within hundreds of millions of years. The fact that intermediate mass black hole candidates still exist near Sagittarius A star presents a puzzle. If they arrived billions of years ago through galaxy mergers or globular clustering spiral, they should have merged with the central black hole by now. Their continued existence requires explanation. One possibility is recent arrival. The Milky Way continues to merge with smaller galaxies today. The Sagittarius dwarf galaxy is currently being torn apart by our galaxy's tidal forces, with its stars being incorporated into the Milky Way's halo. If the Sagittarius dwarf contained an intermediate mass black hole, that object might have reached the galactic center only recently, not yet having had time to spiral all the way in to merge with Sagittarius A star. Another possibility is that the in-spiral timescale is longer than simple calculations suggest. Dynamical friction calculations assume a smooth stellar background, but the galactic center is anything but smooth. Dense star clusters, massive molecular clouds, and complex gravitational potentials could modify the friction process in ways that extend the in-spiral time. Relativistic effects near the supermassive black hole might also alter the dynamics in ways that current models do not capture. A third possibility involves continuous resupply. If intermediate mass black holes form regularly throughout the galaxy, and a fraction eventually reach the galactic center, the population might be maintained in steady state. New arrivals would replace objects that merge with Sagittarius A star, keeping the intermediate mass black hole population roughly constant over time. Each of these possibilities has implications for gravitational wave astronomy. Black hole mergers produce gravitational waves that propagate through spacetime at the speed of light. The amplitude and frequency of these waves depend on the masses of the merging objects and the dynamics of their final in-spiral. Intermediate mass black holes, merging with Sagittarius A star, would produce gravitational wave signals in a frequency band that current detectors cannot access but future instruments will target. The rate of such mergers determines how often gravitational wave observatories might detect events from galactic centers. If intermediate mass black holes are common and merge on relatively short timescales, the cumulative gravitational wave emission from all galaxies in the universe would produce a detectable background signal. Current limits on this background already constrain merger rates, and future observations will provide much tighter constraints. The discovery of a larger stellar population in the central parsec than previously known challenges models of how stars survive near a supermassive black hole. Stars in the galactic center experience extreme conditions that should limit their lifespans. Gravitational encounters with other stars occur frequently in such a dense environment. Close passages cause tidal heating that might strip material from stellar surfaces or even trigger merger events. Radiation from the black hole's accretion flow, even in its current low state, bathes the stellar population in X-rays and ultraviolet light. This radiation could evaporate stellar atmospheres over extended periods, gradually stripping mass from stars and shortening their main sequence lifetimes. Stars that would live billions of years in quiet galactic regions might survive only millions of years near the galactic center. Yet Webb found more stars near Sagittarius, a star than expected, suggesting survival is easier than models predicted. The stellar census exceeded previous estimates by factors of 5 or more. Either the destruction processes are less efficient than assumed, or new stars are being added to the population faster than old stars are being removed. Perhaps stars in the central parsec formed recently and have not yet been destroyed. If ongoing star formation replenishes the population, a large stellar count could be maintained even if individual stars have short lifespans. The protostars Webb detected support this interpretation. Star formation near the black hole might be continuous rather than episodic, maintaining a young stellar population in dynamic equilibrium. Perhaps the encounter rate is lower than assumed because stellar orbits are more aligned than random. If stars near the galactic center tend to orbit in similar planes rather than isotropically, they would encounter each other less frequently. Such orbital alignment could result from star formation in a disk configuration or from dynamical evolution that preferentially removes stars on high-inclination orbits. Webb observations of stellar proper motions can test whether such alignment exists. Perhaps the black hole's radiation output has been even lower historically than we observe today. If Sagittarius A star has been exceptionally quiet for millions of years, the stellar population would have experienced less radiation damage than models assuming typical activity levels would predict. The relic ionization evidence suggests past activity, but activity levels might still have been lower on average than assumed in stellar evolution calculations. The expanded stellar census also reveals information about the stellar initial mass function near the galactic center. The initial mass function describes how the masses of newly formed stars distribute across different size ranges. In most environments, low-mass stars outnumber high-mass stars by factors of hundreds. For every star like our Sun, roughly 100 stars less massive than half a solar mass form, while only one star in several thousand exceeds 10 solar masses. But the galactic center might have a different initial mass function biased toward more massive stars. Theoretical arguments suggest that the unusual conditions near a supermassive black hole could shift star formation toward higher masses. The intense radiation field heats gas and prevents small clumps from collapsing. Only the most massive clumps, which would form the most massive stars, can overcome the thermal pressure and complete gravitational collapse. A top-heavy initial mass function would help explain the presence of young massive stars near Sagittarius A star. If star formation in the galactic center preferentially produces massive stars rather than the usual mix, the young stars we observe might be the dominant population rather than an anomalous subset. Understanding why the initial mass function would differ in the galactic center connects to fundamental questions about how stellar masses are determined during the collapse of gas clouds into stars. Webb's observations of gas outflows from the galactic center constrain models of feedback between supermassive black holes and their host galaxies. Feedback refers to how energy released by black hole activity influences star formation throughout a galaxy. This concept has become central to understanding galaxy evolution because simulations without feedback produce galaxies that look nothing like real ones. In simulations lacking feedback, gas cools and collapses too efficiently. Galaxies form too many stars too quickly, producing stellar populations far more massive than observed. The simulations produce compact, overly dense galaxies rather than the extended spiral and elliptical systems we see in the real universe. Something must prevent gas from cooling and forming stars as efficiently as pure gravitational physics would predict. Feedback from supermassive black holes provides a natural solution. When black holes accrete matter, they release energy in various forms. Radiation pressure can push gas away from the galactic center. Jets of relativistic particles can drill through galactic gas, depositing energy across enormous distances. Winds driven by radiation or magnetic fields can sweep up material and expel it from the galaxy entirely. The outflow velocities measured by Webb exceed simple models of radiation-driven winds. The gas racing away from the galactic center moves faster than radiation pressure alone can explain, at least given the current luminosity of Sagittarius A star. Either the mechanical energy input from the black hole is larger than its current luminosity suggests, or additional energy sources contribute to accelerating the outflow. Supernovae near the galactic center could provide additional energy. The massive stars in the central region explode as supernovae at rates much higher than the galactic average. Each supernova releases roughly 10 to the 51 ergs of energy, enough to accelerate substantial amounts of gas to high velocities. The cumulative effect of many supernovae could drive the outflow even without significant contribution from the black hole itself. The chemical composition of the outflowing gas provides clues about its origin. Material synthesized in stellar interiors and ejected by supernovae has different abundance patterns than material directly accreted onto the black hole and expelled through radiation pressure. Supernovae enrich their ejecta with heavy elements like iron, silicon, and oxygen produced by nuclear fusion in massive stars. Outflows driven by black hole activity would have compositions closer to the ambient interstellar medium, which contains lower fractions of these heavy elements. Webb's spectroscopy revealed that the outflowing gas is indeed enriched in heavy elements, suggesting significant supernova contribution. The outflow carries processed material from stellar deaths toward the Fermi bubbles and potentially beyond the galaxy itself. This enriched material will eventually mix with intergalactic gas, spreading the products of stellar nucleosynthesis across cosmic voids. Understanding galactic center outflows helps explain the Fermi bubbles and other large-scale structures extending from the Milky Way's central region. The energy required to inflate these bubbles could come from sustained low-level outflows over millions of years, or from short-duration high-power events. Webb's measurements of current outflow properties, combined with models of how those properties evolved over time, constrain which scenarios can explain the observed structures. The theoretical implications of Webb's galactic center discoveries extend beyond our own Milky Way. Every large galaxy harbors a supermassive black hole. If the physical processes Webb revealed near Sagittarius A star operate in other galactic centers, our understanding of galaxy evolution throughout cosmic history requires revision. Distant galaxies cannot be studied in the detail Webb achieves for the Milky Way's center. Individual stars remain unresolved at distances of millions of light-years. Gas dynamics appear only in coarse averages smoothed over scales larger than entire stellar populations. The detailed physics operating within light-years of distant supermassive black holes remains hidden behind the fundamental resolution limits of any telescope humanity might conceivably build. But the physical insights gained from the galactic center can be applied to interpret observations of distant systems. If star formation can occur near our supermassive black hole despite theoretical prohibitions, perhaps similar processes operate in other galaxies, with important implications for their stellar populations and evolution. If intermediate mass black holes are common near Sagittarius A star, they might be common in other galactic centers as well, affecting gravitational wave predictions and black hole growth models. The galactic center was supposed to be well understood. Decades of observations had built a consistent picture of a quiet, supermassive black hole surrounded by old stars in a relatively static environment. Webb revealed that nearly every element of this picture was incomplete or wrong. The black hole's environment is dynamic, complex, and harboring processes that challenge our theoretical frameworks at the most fundamental levels. Science advances when observations contradict predictions. The discoveries at the galactic center represent exactly this kind of advance, forcing reconsideration of principles that seemed established beyond doubt. The comfortable assumptions of pre-Webb galactic center physics must give way to new frameworks that can accommodate the unexpected observations. The next several years will bring intensive theoretical efforts to incorporate Webb's discoveries into comprehensive models of galactic center physics. Some existing theories will survive with minor modifications. Others will require fundamental revision. Entirely new theoretical frameworks may emerge from the collision between observation and theory that Webb has catalyzed. The ultimate resolution may take years to achieve, but the journey toward understanding has already begun. Every theoretical paper attempting to explain the protostars, the ionized neon, the water vapor, and the intermediate mass black hole candidates represents a step toward a new understanding of how the universe operates in its most extreme environments. The center of our galaxy has become the most important laboratory in astrophysics, and the experiments are just beginning. Sagittarius A star is quiet. Too quiet. A supermassive black hole with 4 million times the mass of our Sun sits at the center of a galaxy containing 400 billion stars and abundant gas. Yet it produces less energy than a modest star factory in one of the Milky Way's spiral arms. This quiescence has puzzled astronomers for decades. Webb's observations have deepened the mystery while providing new clues about what keeps the monster sleeping and what might wake it up. The energy output from Sagittarius A star measures roughly 100 million times less than theoretical maximum for a black hole of its mass. This maximum, called the Eddington luminosity, represents the point where radiation pressure pushing outward balances gravity pulling inward. Active supermassive black holes in distant galaxies routinely approach this limit, outshining their entire host galaxies as they consume vast quantities of matter. These cosmic beacons, called quasars, are visible across billions of light years, announcing the presence of feeding black holes to observers throughout the universe. Our black hole consumes almost nothing. The accretion rate onto Sagittarius A star measures less than 1/1000th of a solar mass per year. To put this in perspective, if you gathered all the matter falling into our supermassive black hole over an entire century, it would amount to less than the mass of a small asteroid. At this rate, the black hole gains negligible mass over cosmic timescales. The galaxy provides abundant potential fuel in the form of gas clouds and stellar winds, yet something prevents that fuel from reaching the event horizon. This starvation diet seems impossible given the environment. The mini-spirals contain thousands of solar masses of gas orbiting within light years of the black hole. Stellar winds from massive stars near the galactic center inject additional material continuously. The raw ingredients for vigorous accretion exist in abundance. Yet Sagittarius A star refuses to eat. Webb's detailed observations of gas flows near Sagittarius A star reveal part of the answer. The gas spiraling toward the black hole is remarkably hot. Temperatures exceed 10 million degrees in the innermost regions accessible to observation. At these temperatures, gas pressure resists gravitational compression and prevents material from falling efficiently onto the black hole. The gas forms a puffy, diffuse structure rather than the thin, dense disk that would channel matter rapidly toward the event horizon. Compare this to actively feeding black holes in distant galaxies. Those systems contain thin accretion disks, where gas cools efficiently through radiation. The cooled gas settles into a flattened configuration that spirals inward on relatively short timescales. Energy released during the infall escapes as brilliant radiation visible across cosmic distances. The process is efficient, converting roughly 10% of the infalling mass into radiated energy, according to Einstein's famous equation relating mass and energy. Sagittarius A star operates completely differently. This hot, diffuse state results from a process called advection-dominated accretion flow. Energy released by gravitational compression heats the gas faster than radiative processes can cool it. The trapped heat keeps the gas expanded and prevents efficient accretion. Material technically spirals inward but does so slowly, with most of the gravitational energy carried into the black hole as heat rather than radiated away as light. The physics resembles what happens when you compress air in a bicycle pump. The compression heats the air, and unless that heat escapes quickly, the pressure builds and resists further compression. Near Sagittarius A star, the gas heats as it falls inward, but the density is too low for efficient radiation. The heat stays trapped, puffing up the flow and preventing the formation of a thin disk. Webb's spectroscopic observations provided the first detailed measurements of gas temperatures and densities in the advection-dominated flow around Sagittarius A star. The data confirm that theoretical models correctly describe the basic physics, while revealing unexpected complexity in the flow structure. The accretion flow is not smooth and symmetric, but instead contains turbulent eddies and density variations that occasionally allow clumps of material to fall toward the black hole more rapidly than average. The turbulence creates a constantly shifting landscape of hot and cool regions, dense patches and rarefied voids. Material follows chaotic trajectories rather than smooth spirals. Some gas gets flung outward by turbulent motions before it can reach the black hole. Other material finds pathways through the chaos that carry it inward more efficiently. The result is an accretion flow that varies unpredictably on timescales of hours to days. These density variations could explain the small flares occasionally observed from Sagittarius A star. Several times per day, the black hole brightens briefly in X-rays and infrared light before returning to its quiescent state. The brightenings typically last tens of minutes to a few hours, increasing the luminosity by factors of 10 to 100 before fading back to baseline. These flares have been monitored for decades, but their origin remained uncertain. Webb observed several such flares during its Galactic Center monitoring campaign, capturing their spectral evolution with unprecedented detail. The telescope watched as the emission rose, peaked, and declined, recording changes in temperature and composition throughout each event. No previous observatory had the combination of sensitivity and spectral resolution needed to track flare evolution so precisely. The flare spectroscopy revealed that brightening events involve both increased thermal emission from hot gas and non-thermal emission from particles accelerated to relativistic speeds. The thermal component shows temperatures exceeding 100 million degrees, far hotter than the ambient accretion flow. The non-thermal component indicates electrons moving at significant fractions of light speed, radiating through a process called synchrotron emission as they spiral through magnetic fields. The acceleration mechanism likely involves magnetic reconnection, a process where twisted magnetic field lines suddenly snap and release their stored energy. Magnetic fields threading through the accretion flow become wound and tangled by the turbulent motions. Eventually, the field configuration becomes unstable, and the lines reconnect in a different pattern. The energy stored in the twisted configuration gets released suddenly, heating gas and accelerating particles to extreme velocities. Similar processes produce solar flares on our Sun, but the energies involved near Sagittarius A star are billions of times greater. A typical flare from our supermassive black hole releases more energy than our Sun produces in an entire year. These events are small only in comparison to the enormous energies available in principle from such a massive black hole. By any terrestrial standard, they represent cataclysmic explosions occurring multiple times daily at the heart of our galaxy. Understanding why Sagittarius A star remains quiet most of the time matters for predicting whether it might become active in the future. The current quiescent state could be permanent, reflecting a fundamental change in the black hole's environment that cut off the fuel supply indefinitely. Perhaps the galaxy has matured to the point where gas no longer flows toward the center in sufficient quantities to support significant accretion. Perhaps feedback from past activity cleared the central region of dense gas that might otherwise fall toward the black hole. Or the quiescence could be temporary, a pause between more active episodes that occurred in the past and will occur again in the future. The universe contains many examples of black holes that transition between active and quiet states. Some active galactic nuclei show variability on timescales of years to decades, fading from brilliance to obscurity and sometimes returning to activity. If Sagittarius A star follows similar patterns, the current quiet phase might represent a temporary lull rather than permanent dormancy. Evidence for past activity comes from multiple sources that paint a picture of a black hole with a violent history now hidden behind present tranquility. The Fermi bubbles, spanning 50,000 light-years from tip to tip, above and below the galactic plane, require enormous energy input to inflate. These structures contain hot gas at temperatures of tens of millions of degrees, energetic cosmic ray particles, and magnetic fields that produce gamma-ray emission detectable from Earth. The energy contained in the Fermi bubbles exceeds the total output of our Sun over its entire 10 billion-year lifetime by factors of millions. Something injected this energy into the galactic halo within the past few million years. The most likely energy source is past activity from Sagittarius A star, perhaps a period when the black hole consumed matter at rates thousands or millions of times higher than today. Alternative explanations involving concentrated star formation near the galactic center can contribute, but struggle to explain the full energy budget. Supernovae from massive stars release enormous energy, but producing the Fermi bubbles through supernovae alone would require star formation rates exceeding anything observed in the galactic center region. The bubbles point toward past black hole activity as the primary inflation mechanism. Radio observations reveal additional structures that might represent fossil evidence of past energetic outbursts. The galactic center lobe extends roughly 500 light-years perpendicular to the galactic plane. The galactic center arc shows a peculiar linear structure that might trace magnetic fields energized by past activity. These features could represent snapshots of outbursts at various times in the black hole's history, preserved in the structure of gas and magnetic fields surrounding the galactic center. X-ray observations provide more recent evidence that Sagittarius A star was significantly more active within historical timescales. The X-ray reflection nebula near the galactic center shows fluorescent ion emission that requires illumination by a powerful X-ray source. When X-rays strike ion atoms in molecular clouds, they knock electrons from inner atomic shells. As other electrons cascade down to fill these vacancies, the atoms emit characteristic X-ray fluorescence. The pattern of fluorescent emission across the galactic center region reveals how X-ray illumination has varied over time. X-rays travel at light speed, so clouds at different distances from the black hole reflect X-rays from different times in the past. By mapping the fluorescence, astronomers can reconstruct the X-ray output of Sagittarius A star over the past several centuries. The reconstruction shows that the black hole was millions of times more luminous within the past 300 to 400 years than it is today. The implied luminosity approached that of modest active galactic nuclei, far exceeding anything observed from Sagittarius A star during the era of modern astronomy. The black hole apparently experienced a significant outburst within the past few centuries and has since returned to its current quiescent state. This recent activity provides crucial context for Webb's observations. The black hole we observe today is not in its typical state, but rather in an unusually quiet phase following relatively recent activity. The triggers and timescales of such transitions remain poorly understood, but the evidence confirms that Sagittarius A star can switch between quiet and active modes on timescales relevant to human civilization. If such transitions can occur within centuries, what triggers them? The most likely culprit involves variations in the fuel supply reaching the innermost accretion flow. Gas clouds occasionally pass close enough to Sagittarius A star to be tidally disrupted and partially consumed. Stars can venture onto orbits that carry them within the tidal radius, suffering destruction that feeds the black hole. Even the accretion flow itself might experience instabilities that periodically channel material inward more efficiently. Webb detected several gas clouds and stellar objects on trajectories that will bring them close to Sagittarius A star within the coming decades. These objects represent potential triggers for future activity. Monitoring their approaches will reveal whether close passages actually produce increased emission from the black hole. One object designated G2 has been monitored for over a decade as it approaches and recedes from the black hole. Initially discovered in 2011, G2 appeared to be a pure gas cloud on a trajectory that would carry it within 200 astronomical units of Sagittarius A star. At this distance, well inside the tidal radius, the cloud should have been stretched and disrupted, potentially producing a feeding event observable across the electromagnetic spectrum. Astronomers around the world watched as G2 approached closest passage in 2014. Many expected spectacular fireworks as the cloud was torn apart and consumed. Instead, G2 survived its closest approach largely intact, emerging from the encounter stretched but not destroyed. The survival suggests that G2 contains a dense stellar core hidden within a dusty envelope. The core's gravity held the object together through the tidal stresses that would have destroyed a pure gas cloud. G2's survival disappointed those hoping to witness a feeding event, but provided valuable information about objects orbiting near the black hole. Similar objects await their closest approaches in coming years and decades. Some might be pure gas clouds that will be disrupted, others might contain hidden stellar cores that allow survival. Each close passage represents an experiment that reveals how the black hole interacts with material in its vicinity. The star S2 makes its closest approach to Sagittarius A star every 16 years. During these passages, the star experiences extreme tidal forces that might strip small amounts of material from its outer atmosphere. This stripped material could contribute to feeding the black hole, though the amount involved is small compared to the dramatic tidal disruption of an entire star. S2's next close approach occurs in 2034. Webb, or its successors, will observe this passage with capabilities far exceeding any previous close approach observations. The detailed monitoring might reveal whether tidal stripping actually occurs and how the stripped material affects the black hole's emission. Eventually, statistical inevitability will deliver a star directly into Sagittarius, a star's tidal radius. Stars in the galactic center follow chaotic orbits that evolve through gravitational encounters with other stars. Occasionally, these encounters scatter a star onto an orbit that passes inside the tidal radius. The star then experiences tidal forces exceeding its structural integrity and gets torn apart. The resulting tidal disruption event would produce a dramatic brightening lasting months to years as stellar material spirals into the black hole. The disrupted star provides fuel for accretion at rates millions of times higher than current levels. The black hole's luminosity would increase correspondingly, potentially making the galactic center visible to naked eye observers despite the intervening dust. Such events are observed in distant galaxies at rates of roughly 1 per 100,000 years per galaxy. Given this rate, the Milky Way should experience a tidal disruption event within the next few 100,000 years on average. The last such event might have occurred tens of thousands of years ago, long before humans developed the technology to observe it. When the next tidal disruption event occurs, our galactic center will blaze with luminosity millions of times its current output. The brightening will be detected first at X-ray wavelengths that can penetrate the intervening dust. Within weeks, infrared emission will increase dramatically. The event will persist for months to years before gradually fading as the supply of stellar debris exhausts. What would a major awakening of Sagittarius A star mean for the Milky Way and for Earth? The direct effects at our distance of 26,000 light-years would be modest but detectable. The radiation from an active Sagittarius A star would need to penetrate the same dust clouds that currently block our view. Optical and ultraviolet light would be absorbed, protecting Earth from the most dangerous wavelengths. X-rays and gamma rays would also be attenuated, though more of this high-energy radiation would reach Earth than visible light. The night sky might brighten noticeably, with the galactic center region becoming visible to the naked eye through breaks in the dust. The diffuse infrared emission from heated dust would increase substantially. Radio astronomers would detect dramatic changes in the emission from the galactic center. But dangerous radiation levels at Earth's surface are unlikely unless the activity reached truly extreme levels sustained over long periods. The more significant effects would be indirect. An active Sagittarius A star would drive powerful outflows that could interact with the interstellar medium throughout the central regions of the galaxy. Gas clouds, thousands of light years from the black hole, would feel the increased radiation pressure and particle bombardment. Star formation rates might change in response to heating or compression of molecular clouds. The cosmic ray flux from particle acceleration near the black hole could increase throughout the galaxy. Cosmic rays are protons, and heavier atomic nuclei accelerated to near light speed by extreme astrophysical processes. They travel through the galaxy along twisted paths determined by magnetic fields, eventually reaching every corner of the Milky Way, including Earth. Increased cosmic ray production near an active Sagittarius A star would raise the cosmic ray flux experienced throughout the galaxy over timescales of millions of years. Elevated cosmic ray flux has biological and technological consequences. Cosmic rays contribute to mutation rates in living organisms by damaging DNA. They also affect electronics by causing bit flips in computer memory and damaging sensitive components. Modern technology already contends with cosmic ray effects, designing radiation-hardened systems for critical applications. A significant increase in the cosmic ray flux would require additional protective measures. For any civilizations inhabiting the inner galaxy, closer to Sagittarius A star than Earth, the effects of an awakening would be far more dramatic. The radiation environment would become much more hostile. X-rays and ultraviolet light that dust blocks from reaching Earth would illuminate planets in the central regions directly. Habitable zones around stars might shift as planetary atmospheres respond to increased energy input. Planets within a few thousand light-years of the galactic center might experience conditions comparable to being near an active galactic nucleus. Such environments are generally considered hostile to complex life. The intense radiation would strip planetary atmospheres, sterilize surfaces, and destroy any biospheres that had developed during quieter periods. Advanced civilizations in the inner galaxy might need to take protective measures or relocate to avoid the worst effects of an awakened black hole. They might construct shields to block dangerous radiation. They might migrate to planets farther from the galactic center. They might burrow underground or underwater to escape surface radiation. The most advanced civilizations might even attempt to influence the black hole's activity directly, though how such influence might be achieved remains purely speculative. This raises the question of whether civilizations throughout the Milky Way have already experienced such effects. Sagittarius A star has existed for most of the galaxy's 13 billion year history. Over this vast span of time, the black hole has likely experienced numerous active phases interspersed with quiescent periods like the present. The Fermi bubbles alone suggest major activity within the past few million years, a blink of an eye in cosmic terms. Any long-lived civilizations in the inner galaxy would have witnessed these transitions repeatedly. Their survival would require adaptation to dramatically changing conditions on timescales of thousands to millions of years. They would need technological or biological mechanisms to weather the storms of black hole activity and rebuild during quiet intervals. Perhaps intelligent life avoids the inner galaxy precisely because of this hazard. The habitable zone for civilizations might extend only to certain distances from supermassive black holes, beyond which the risks of periodic activity become manageable. Earth's location in the outer spiral arms might be favorable for the development of complex life, not despite being far from the galactic center, but because of it. For humanity, still confined to a single planet and lacking the capability to observe the galactic center in real time, the awakening of Sagittarius A star would be detected only through changes in the radiation reaching Earth. Given the 26,000 light-year distance, any activity we observe today actually occurred before written history began. The light reaching Webb's detectors left the galactic center when humans were still living in the last ice age, before agriculture, before cities, before any of the achievements that define civilization. This temporal uncertainty creates a strange relationship between humanity and the supermassive black hole at the heart of our galaxy. We cannot know the current state of Sagittarius A star. We can only observe its past and extrapolate from theoretical understanding. The black hole might have awakened centuries ago, with evidence of its activity racing toward Earth through the cosmic dust. We would have no warning until the radiation arrives. Conversely, activity we observe today has already concluded from the perspective of any observers near the galactic center. The flares Webb detected have long since faded. Any responses to those flares by material or beings near the black hole have already occurred, evolved, and potentially dissipated. We are always observing history, never the present. Webb's observations contribute to understanding this uncertainty by revealing the ingredients for potential future activity. The gas clouds approaching the black hole, the instabilities in the accretion flow, the dense stellar environment where tidal disruptions might occur, all of these factors influence the probability of significant activity. By studying these ingredients in detail, astronomers can make improved predictions about the likelihood and timing of future events. The cosmic perspective on Sagittarius A star extends beyond our own galaxy to encompass the entire universe of supermassive black holes. Every large galaxy contains such an object at its center. Many of these black holes are actively consuming matter, powering the brilliant quasars visible across billions of light years. Others, like our own, sit in relative quiescence. Understanding what determines a black hole's activity state helps explain the diversity of galactic properties observed throughout the cosmos. The fraction of galaxies hosting active black holes changes with cosmic time. In the early universe, active galactic nuclei were far more common. The cosmic dawn saw supermassive black holes consuming matter at prodigious rates, their light outshining the young galaxies hosting them. Over billions of years, the activity declined as galaxies matured and gas supplies diminished. The modern universe contains fewer active nuclei, with most supermassive black holes in states similar to our own. This evolutionary pattern suggests that Sagittarius A star was once far more active than we observe today. The Milky Way formed roughly 13 billion years ago from the merger of smaller proto-galaxies. During its early history, the central black hole likely consumed matter at rates comparable to distant quasars. The transition to quiescence probably occurred billions of years ago, as the galaxy stabilized and gas flows toward the center diminished. Webb's observations of the current environment around Sagittarius A star provide a snapshot of conditions at this late evolutionary stage. The quiet black hole, the hot advection-dominated accretion flow, the occasional flares, all represent the end state of evolution from a violent active past to a subdued present. The discoveries at the galactic center also influence humanity's understanding of our cosmic place and fate. We inhabit a galaxy governed by a supermassive black hole that shapes galactic structure through its gravity and occasional energetic outbursts. Our position in the outer spiral arms shields us from the most intense effects of activity near the galactic center, but we remain connected to the black hole through the shared gravitational system binding the Milky Way together. Every star in our galaxy, including our Sun, orbits around the galactic center of mass dominated by the supermassive black hole and the dense stellar cluster surrounding it. Our solar system completes one orbit every 230 million years, a period sometimes called a galactic year. Over the Sun's 4.5 billion year history, we have completed roughly 20 galactic orbits, witnessing countless changes in the galactic environment, including likely periods of enhanced activity from Sagittarius A star. The eventual merger between the Milky Way and Andromeda will bring dramatic changes to the galactic center environment. As the two galaxies collide over the next 4 to 5 billion years, their structures will be transformed through gravitational interactions. Stars will be flung onto new orbits. Gas clouds will be compressed and stirred. The two central black holes will begin a long journey toward each other. Andromeda's central black hole weighs roughly 100 million solar masses, about 25 times more massive than Sagittarius A star. When the galaxies merge, both black holes will sink toward the common center through dynamical friction, the same process that causes intermediate mass black holes to spiral inward. The inspiral will take hundreds of millions of years, with the black holes orbiting each other in an ever-tightening dance. Eventually, the two black holes will merge, producing the most powerful gravitational wave event our local cosmic neighborhood will ever experience. The gravitational waves from this merger will propagate across the universe, detectable by instruments throughout the cosmos. The energy released in gravitational waves will exceed the combined luminosity of all the stars in both galaxies at the moment of merger. The merged black hole will weigh over 100 million solar masses, combining the masses of both progenitors minus a few percent radiated away as gravitational waves. This combined monster will inherit the gas and stellar populations from both galaxies, potentially experiencing periods of renewed activity as material from the collision finds its way to the new galactic center. The merger might trigger a new active phase as gas from both galaxies funnels toward the combined center. For millions of years, the merged system might shine as a quasar, visible across cosmic distances. Any civilization surviving the merger would witness the awakening of a black hole far more massive and potentially far more active than Sagittarius A star has been in billions of years. Earth will not witness this spectacle in its current form. Our planet will be uninhabitable by then due to the Sun's evolution into a red giant roughly 5 billion years from now. The Sun will expand to engulf Mercury and Venus, and while Earth might survive, its surface will be sterilized by the increased luminosity long before the actual expansion occurs. Any descendants of humanity observing the galactic merger will do so from wherever they have relocated. Those observers will witness a transformed night sky. The two spiral galaxies will merge into a single elliptical galaxy lacking the organized spiral arms that characterize the Milky Way today. The stellar populations will mix and blur into a smooth distribution surrounding the combined supermassive black hole. The orderly rotation of the current Milky Way will give way to chaotic stellar orbits pointing in all directions. The discoveries from Webb's galactic center observations remind us that the universe operates on scales and timescales beyond human intuition. A supermassive black hole 4 million times the Sun's mass occupies the center of our galaxy. Stars form in hostile environments where theory says they cannot survive. Gas flows and outbursts shape galactic structure across thousands of light years. The monster at the heart of the Milky Way influences everything from the orbits of individual stars to the fate of civilizations that might inhabit distant worlds. We have taken the first clear look at this cosmic engine with eyes capable of seeing through the dust that has hidden it since the beginning of human awareness. Webb demonstrated that the galactic center harbors complexities we are only beginning to comprehend, processes that operate beyond the boundaries of comfortable theory. The sleeping giant may not wake in human lifetimes, but it will wake eventually. The processes governing its slumber and awakening connect to fundamental questions about how galaxies form, evolve, and determine the destinies of any life that emerges within them. 26,000 light-years away, in the direction of the constellation Sagittarius, lies a region where space-time curves so severely that not even light can escape. Around this gravitational prison orbits a swarm of stars moving at millions of miles per hour, gas clouds spiraling toward oblivion, protostars forming where theory says they cannot exist, and perhaps intermediate mass black holes destined to merge with the central monster. This is the heart of our galaxy, the center around which everything we know orbits, the gravitational anchor holding 400 billion stars together across 100,000 light-years of space. Webb has shown us this heart as never before. The image is more complex, more dynamic, more mysterious than anyone expected. The answers Webb provided have generated new questions that will drive astronomical research for decades. And somewhere in the cascade of discoveries, we may find insights that illuminate not just the galactic center but our own existence as temporary patterns of matter in a universe ruled by gravity, time, and the monsters that lurk at galactic hearts. The center of the Milky Way was supposed to be a solved problem. It is not. The supermassive black hole was supposed to be dormant. It is, but perhaps not permanently. The equations were supposed to predict what we would find. They fell short. Webb has opened a window onto the most extreme environment accessible to detailed human study, and what we see through that window demands that we reconsider nearly everything we thought we knew. The monster at the center sleeps, but it dreams. The flares that punctuate its slumber, the gas clouds spiraling ever closer, the stars forming impossibly in its shadow, all represent glimpses into dreams that span millions of years and involve energies beyond human comprehension. And in those dreams lie secrets about the universe that we are only beginning to uncover. The James Webb Space Telescope has given us our first clear glimpse into those dreams. What we have seen has shattered assumptions, revealed unexpected complexity, and opened pathways to understanding that will occupy astronomers for generations. The galactic center is no longer a distant abstraction glimpsed through veils of cosmic dust. It is a living, dynamic environment where the most extreme physics in the accessible universe plays out around a gravitational monster that has shaped our galaxy since its formation and will determine its fate long after our sun has died. We are connected to this monster through gravity, through history, through the cosmic processes that created the atoms in our bodies and the planet beneath our feet. The heavy elements forged in stars near the galactic center have spread throughout the galaxy over billions of years, eventually incorporating into the molecular clouds that collapse to form our solar system. We are made, in part, of matter processed through the extreme environment Webb has revealed. This connection gives the discoveries meaning beyond pure scientific curiosity. Understanding the galactic center means understanding our origins and our place in a universe of awesome scale and power. The sleeping giant at the heart of the Milky Way is not just an astronomical object to be studied. It is the engine that has shaped our cosmic home and will continue shaping it long after humanity's brief moment in cosmic history has passed. Webb has shown us that engine as never before. The view demands humility, inspires wonder, and reminds us that the universe contains mysteries enough to occupy curious minds for as long as curious minds exist to contemplate them. The monster sleeps, but it will wake. And when it does, the galaxy will know that the heart of the Milky Way has stirred once more.